Okay, so I'm going to introduce Anka, who's going to be our chair, our fearless chair for the session.
Thank you. Can I borrow your, can you hear me? Yeah. Okay, good, the mic's not on. Good, welcome to the second session. This is a session titled Novel Applications and Human-Robot Interaction. And in true wafer style, it's really about planning, but it's about interesting aspects of planning that involve planning for drawing, planning with language, planning with people, and so on. So our first speaker is Ahalya Prabhakar, nice. And she's going to be talking about planning motion for robots that can actually draw and sketch.
Thank you all for being here. Today I'm going to talk about a new way to approach and solve control problems for a certain task that comes from my work to enable robots to draw. So historically, we're really good in robotics at designing and controlling robotic systems for air regulation to do tasks such as point-to-point maneuvering and motion planning. However, there are some tasks that don't necessarily fall under this type, and drawing is just an example of one of them. So if we want to think about how we draw, we typically think of communicating visual information from the original image to the viewer through these physical motions of drawing. And so if we want to actually do it, we somehow have to visualize the image, process it to figure out how to recreate it, and the motions needed to actually create the recreation, and then render the drawing. And when you want to enable a robot to do the same, such as here when I've enabled my Baxter robot to draw a portrait of Abraham Lincoln, we follow these same steps of visualizing, processing, and then rendering the drawing to actually communicate this visual information. However, before I go any further, I have to ask, why do we care about getting robots to draw, and what makes drawing such an interesting task for robots to do? Well, first, other than the fact that robotic art is just cool, the task of drawing is fundamentally different from many of these standard tasks we typically think of robots actually doing. Unlike many of these trajectory, error-driven tasks, where error at any single point in time matters a lot for the performance of the task, drawing, on the other hand, is an example of a task where error at any single point doesn't really affect the success or failure of the task, or to be able to see whether we've actually correctly drawn what we're trying to draw. Instead, it's this accumulation of error over the entire trajectory, or really the spatially distributed objective that matters much more to see whether we've correctly drawn what we're trying to draw and achieved our goal. In addition to the fact that it's a slightly different objective that we're trying to achieve, there's also the fact that there's many ways to achieve the same goal when we're trying to draw. So if I got every person in here to draw the Eiffel Tower or the Taj Mahal, or even let's just say a house, every person in here would do it differently. Some people would start with the frame, then do the roof before filling in doors and windows. Others might do it in the opposite direction. And yeah, even though all of our approaches and our motions that we use to render the drawings are different, hopefully by the end of our drawings, we all have drawn the same image and have successfully communicated the same information. So these two main parts, or these two main kind of caveats, make the fact that mean that some of the standard ways that we approach drawing and other similar tasks might actually be not necessarily the best way to do so. So, and this isn't just true for drawing. Drawing is just one of a whole family of tasks where it's true. Things like cleaning, for example, where instead of there may not be a single correct path to follow, but instead it may depend on a spatial distribution of where the dirt is in the room or wherever you're trying to clean. Or things like food preparation, where stirring may not depend on the state at a single point in time, but really the overall consistency over the entire distribution of whatever you're trying to stir. Or things like folding laundry, where there are many ways to achieve the same goal. And so the question we're trying to ask and answer is, how can we define the control problem to encompass this idea that there are a family of solutions for a given task, and that instead of focusing on this error in time type objective, we're instead looking at this spatially distributed objective. And so our answer to this problem is to use ergodicity. So ergodicity is a statistical measure that encompasses this idea of relating the solution to the spatially distributed objective. And it does so by relating the time-averaged behavior of a trajectory to the spatial statistics of the probability distribution of the task, so in this case of the image. And the relationship it states is that the time spent in a region of the probability distribution should be proportional to the density of the region. So for example, here, given an original image, we represent it as a spatial distribution, where the more intense the color is in any given region, the higher the density of that region. So if we use the ergodic metric to then create an ergodic trajectory with respect to that distribution, the trajectory should then follow, where we say we spend more time kind of coloring in where there's more color and less time in areas where there isn't. So using the ergodic metric then allows us to set this up as a nice control objective where this is instead our control, instead of saying that this is necessarily the correct motion we have to follow, and then the control simply follow by following that single motion. So now that we see we can use the ergodic control to kind of generate solutions for this task, I wanted to compare it to see, okay, how does it work compared to some of the more existing kind of standards ways that drawing robots typically employ. So the first method I compared to was the one used by this HOAP2 robot that uses a combination of edge detection and image binarization to render the contours of the facial portrait and then the shading that's shown in red there. And the first thing we can see is that the rendering generated by our ergodic control method, which is boxed in purple up at the top, generates like a pretty comparable result, despite the fact that we use far fewer steps. So with the edge detection method, they have to not only use a combination of edge detection and image binarization to do so, but then once they use those steps, they have to post-process those to determine the motions needed to draw the specific contours. And then they used motion primitives to define that the correct ways to shade, and then followed those motions to actually render the shading. Whereas we were able to kind of do so directly from the original image. So it's just we were able to get a much simpler algorithm with a comparably good result. We also compared it to the Paul the Robot drawing method, which uses a combination of salient line extraction and then one of two different shading processes to create the shading in the picture. So their first process uses visual feedback, which is this first Paul 1 rendering. And so they use an external camera to kind of update the belief of what's been drawn and then determine where to shade next. And then they also use computational feedback, which uses primarily internal memory to generate where to shade next. And so once again, with our rendering shown at the far left, it's of course stylistically different, but we get a comparably good result, particularly to the computational feedback. And one thing you can note is obviously their visual feedback rendering is really good. And that's something we're actually looking to work towards, is being able to nicely just incorporate an external camera and visual feedback in our method as well, so that we can also improve our trajectories in real time in order to take into account what's drawn and the effect of that as we create our rendering in order to best approximate the image. So now that we can see that at least, okay, we are able to use ergodic control to achieve our objective and draw in a nice way, we wanted to see what kind of scope and flexibility do we have within ergodic control methods, and how can we use ergodic metrics in different ways. So we compared 3 different ergodic control methods. The first is a closed form solution update log that's based on a short time horizon to generate the next single action to best improve the ergodicity. The second, which was generated in our lab, was using a longer time horizon that also calculates the next single action to improve the ergodicity. And the final is a more standard trajectory optimization method that not only characterizes it over the long time horizon, but it's over the full control trajectory over the full time horizon as well. So given these 3 comparisons, we then wanted to see how do they tackle trying to do the same task. So the first one we tried to see was how to, doing back to the drawing task, or how can we draw the portrait of Abraham Lincoln. And so the first thing we can kind of clearly see is that all 3 ergodic control strategies create radically different solutions to all convey the same information. And in particular, we can see that the 2 middle ones that use a single action controller was able to create a much better approximation where you fill in a lot more of the details. Whereas in this trajectory optimization method on the far right for you guys, you create a much more abstract, basically I would say unrecognizable rendering of Abraham Lincoln. However, if you were to use the exact same methods for a slightly different task where you consider handwriting, so drawing the letter N, we once again see that we create radically different solutions for the same task. However, in this case, all 3 of them, even though all the trajectories themselves are extremely different, they're all recognizably the letter N by the end of the trajectory. And the ergodic metric reflects that, where in this bottom case here, by the end of the trajectory, all the ergodicities of the final trajectories are approximately equal, basically saying that, okay, yes, they've all kind of achieved the goal correctly, whereas in the example on the top, the PTO rendering has an ergodicity that's much higher than the other 2, kind of saying that, oh wait, the difference between that trajectory versus the original image is much greater than the others. And so even though they all do minimize the ergodicity, it still at least captures the differences between the different trajectories. So just in terms of some of our dirty laundry or our weaknesses, what are some of the weaknesses? So as we can see, we can't necessarily predict the effect of the dynamics and the control approach ahead of time. So even though they all, for most of these tasks, using an ergodic coding does make sense, the particular way with which we optimize with respect to it, or like the particular ergodic control approach we use, may not be known, and the effect of the choice of it may not be known until you actually try it and you see which works best. So for example, in the case of PTO, where it doesn't actually work very well for something like drawing, it actually may lend itself particularly well to handwriting, where it's kind of more like smooth and overall efficient nature over the full trajectory, lends itself to capture the global reasoning about the shape to kind of generate the most human-like handwriting, the way we would draw the letter N typically. And in addition, this is, if we want to apply this to other tasks and other problems, as the dimensionality of the problem increases, the computations analogously increase exponentially. So that is something to consider where, the computations do get more complex as the dimensionality of the problem increases. So just as a conclusion, we were able to see here that the drawing is only one example of a whole variety or family of spatially distributed tasks, and using ergodicity and ergodic control is a way to essentially address this and a nice way to solve these problems. And it's able to do so in a nice way and create comparably good results in a much simpler algorithm compared to many of the existing ones where they have to basically predefine a lot of the processing of the image as well as the processing of the motions and then try to match that trajectory. We were able to do so in a much smoother and much more simple algorithm, which lends itself to automatability. In addition, we were able to do so without the need for task-specific design of both the hardware and software. There was no need for prior knowledge or human input. And then in terms of parameter tuning, while there is parameters that needed to be tuned, between a whole wide variety of content, we didn't actually have to do any parameter tuning to create a wide variety of images. And then finally, of course, the last thing would be just the fact that the dynamics of the renderer do matter, and how the way the renderer moves does affect the way the rendering actually is processed. And so being able to take into account ergodicity in the control might be the nice way to do it because it does allow for this flexibility in solution. So it's able to capture a wide variety of solutions to achieve the same task. And so, thank you. Do y'all have any questions?
So you used the word controller. I couldn't figure, are you generating a trajectory, or is uncertainty also handled for those of us who have shaky hands?
So we are generating, so in this case, we're generating a trajectory that you're trying to follow. But one of the nice things that I guess is nice with ergodicity is if you were to look at the ergodic metric of, for example, if you drew with a shaky hand, and so there is some uncertainty in your trajectory, it's still reflected where, oh, it's mostly right. And so if you were to do something radically wrong versus something that's mostly right, it would still be okay. So you can almost use it as like a thresholding type scenario where you can still at least use the ergodic metric as an evaluation. So if you use ergodic control as a controller, it creates a trajectory and the control trajectory with it. But if you were to use it as a metric, it at least allows you to actually compare results.
How different would the problem be if you were going to pick up the pen and put it back down?
Well, so actually being able to do that, well, it would be incredibly useful just in terms of getting much better renderings right now. And it's pretty doable. We haven't done it yet. It's something we're working on towards the future. But in terms of achievability, it's not impossible at all. It's fairly doable.
Does it degrade to just dot printing, or?
I mean, it would be interesting to see if that, in some scenarios, it might end up being just dot printing. And it would be really interesting to see if that's what ended up kind of naturally coming out of that problem setup, where it would just naturally lead to that. But
So the trajectories you generate, are they basically open loop trajectories?
yeah, so everything here was open loop, and that's why I was saying one of the things I really want to do, and which our ergodic control algorithm does nicely. It's meant to be allowed to incorporate feedback and stuff. We just haven't done it in this case because it's our first run.
So does your Ergodicity have ways to take into account collisions or objects in between? You can treat the white spaces as objects which you can potentially collide with, so you don't want to go there.
So the ergodic metric itself doesn't, but the way you set up your ergodic control objective could do so, where you maybe set up barrier functions where you're okay, if you go towards there, it's a super high cost there, so it'll naturally want to not go there. So that's what's kind of nice with it, is just using this as the metric within your control objective. You have a lot more flexibility when designing like your control objective to allow you to do things like that, where you can set up the rest of the problem or the rest of the objective to take into account regions like that or tasks.
On the two phases on slide 7, I think, where you were filling in background. Sorry.
Oh no, it's fine. Hold on.
Where you're filling in background in the back, it seemed like there was horizontal artifacts in the one and then vertical artifacts in the other one.
Is it this one?
No, previous.
Yeah, sorry. Let me.
Must be 6.
Can we have the next speaker set up in the meantime? Just like heading over.
Okay, this one?
Yeah, I mean, it almost looks like handwriting on the upper one and then vertical writing on the other one. Were they both printed with the face and the vertical orientation?
I mean, so basically the picture that I input were these two exact, and it's just in vertical. Partially the way.
Is that part of the mechanism that you're using, or is it part of the algorithm that
I
sort of gives these horizontal and vertical?
So I think part of it is the algorithm or the metric itself, the way we kind of encode ergodicity where it generates these. But a lot of it is also just in terms of when you're, for the most of these actions, so these are all single actions, so when you're trying to create the next single best step, typically it would just kind of follow what the closest is, and you get these kind of lines where it's trying to draw, like to best improve the ergodicity for the next single step, it's drawing like the next closest point. So for this particular case, I think it's a combination, but it's primarily the single action.
All right, let's let the next
Sorry.
speaker set up. Thank you.